what is glycogen? So we talked about carbs pretty early on in this semester, so we should be fairly familiar with the kind of language going on here. Glycogen is a polymer consisting of glucose units that have alpha 1 to 4 linkages. So let's review that real quick. We got our alpha, which are basically going opposite directions. And then we're linking the first number 1 carbon to the 4 carbon, starting, of course, from the anomeric carbon. A glycogen has an additional linkage. It is branched. It has an alpha 1 to 6 linkage. So again, we have this alpha connection, and now we're going from the anomeric carbon to carbon number 6. So glycogen has this more complex structure, where it's branching off in many directions, isn't just linear. Let's talk about breakdown of glycogen first, or glycogenolysis. We can break down this glycogen only from one end. So on this previous slide here, we have two ends. We have ends that are kind of at the front. We call those the non-reducing ends. And we have the end, or the back side, and we call that the reducing end. Why do we call them non-reducing and reducing? Well, if you check out the kind of beginning part of the structure, those anomeric carbons don't have a hydroxyl group, okay? Since there isn't a hydroxyl group, it can't be reduced. But this reducing end over here, the anomeric carbon does have a hydroxyl group coming off. That's why it's called a reducing end. When we have this type of structure with a hydroxyl group coming off, what can actually happen is that interconversion between a cyclic and a linear form of the sugar. Don't worry too much about this. Basically, right, if we can interconvert between the cyclic and linear, you'll remember that these types of sugars can be aldoses, can contain an aldehyde, and those are more oxidized forms that can be reduced. Not a super important takeaway. Let's jump into the meat of why we're here. So, these molecules of glycogen are only broken down at the non-reducing end. So we can think of that kind of as the front. There are a lot of these, so we can break down that glycogen really quickly. There are 3 enzymes that perform glycogen breakdown, and they are listed here on this slide. Glycogen phosphorylase, glycogen debranching enzyme, and phosphoglucomutase, which we've kind of already met. The first enzyme is glycogen phosphorylase, sometimes simply called phosphorylase. Here we're breaking down glycogen to units of glucose 1-phosphate, kind of a cousin of glucose 6-phosphate, right? Except the phosphate is coming off of carbon 1, our anomeric carbon. I don't want us to worry about the mechanism. The mechanism seems a little bit complicated if you were to go look into it. But I do want to introduce us to a cofactor that catalyzes this mechanism. So pyridoxal phosphate here, I have the structure on the slide. This phosphate group at the end is actually what's helping us do the doing the catalysis. It helps us do some general acid-base catalysis, so donating protons and taking protons. This enzyme is a major point of regulation for glycogen breakdown. So we're chopping off bits of glucose from glycogen. But this enzyme eventually runs into a problem. Glycogen has branches. what happens when the enzyme gets really close to a branch? Turns out this enzyme can't fit the branch into its active site. It can only fit a linear portion of the sugar. So in comes a secondary enzyme, glycogen debranching enzyme. If we can't deal with the branches, if glycogen phosphorylase can't deal with the branches, well, let's kind of remove the branches. And this enzyme is pretty interesting. So it takes basically the remaining bits of the branch that couldn't be chopped off, and it just plops them on the end of a different branch. There, we have an additional linear part of glycogen that phosphorylase can go ahead and start chewing on. So this enzyme performs that catalysis. Additionally, though, this enzyme can take this last remaining unit of glucose that's stuck and branched, and it can hydrolyze it right off. So this enzyme is super interesting because it actually has two distinctive active sites. One that performs this transfer mechanism, we call that a glycosyl transferase, and then a secondary active site that does the hydrolysis. I think that's pretty cool. So we're chopping up this glycogen into units of glucose 1-phosphate. When we reach a branch, we gotta kind of take that branch, move it somewhere else so we can keep chopping it into glucose 1-phosphate. But glycolysis uses glucose 6-phosphate, so let's make sure to convert the glucose 1-phosphate into glucose 6-phosphate. That's the role of phosphoglucomutase. And the mechanism is really straightforward. We've actually seen this, but now I want us to take a bigger look at it. Now, the mechanism is simplified on this slide. We probably have, a base catalyst coming and taking that proton to give us a better nucleophile. But then we've already seen the mechanism, right? Hydroxyl group deprotonated, great nucleophile attacking our favorite electrophile, the thing that looks like a carbonyl carbon. And actually, it's a bit of a phosphate trade, which we've also seen. So once a phosphate's been taken from the active site of this enzyme, that serine, we know serine can be a decent nucleophile, can go ahead and grab the phosphate on the 1' carbon of this glucose molecule. And after the phosphate trade, we end up with glucose 6-phosphate, which can proceed, apologies, that's a terrible circle, which can proceed right on to glycolysis. To go ahead and give us a bit more ATP.